Welcome everybody, Math 106, Section 4.5, Efficiency, Tolerance, and Percent Change. We're going to start by talking about efficiency. Now machines essentially convert one form of energy to another. It's like a circular saw that takes electrical energy and converts it into rotational motion. But no machine does this perfectly. Some energy is lost along the way. So we have this idea of efficiency. And that's the percentage of the energy that's actually successfully converted into a useful form. The efficiency equation is output energy equals input energy times the efficiency, where the efficiency is some decimal number between 0 and 1. So we're taking this input energy and we're multiplying it by this number. If we multiply it by, let's say, 0.75, that takes our input energy and reduces it by 1/4 into the output energy. So this is the equation we'll be using, the tie equation. I'd like to use O as a variable, but O is often confused with 0, so I try to avoid that. So instead I just use the T for in output, and then input and efficiency. So for the first example, we used a floor buffer that operates at 14% efficiency. It consumes 2,500 joules of energy. We're going to find the actual buffing energy. So the buffing energy is the output. It's the energy output into the circular motion of the floor buffer. The input is given at 2,500 joules. And the efficiency is 14%. So we need to convert 14% into a decimal. We're always convert to a decimal before doing any calculations. So this would be 0.14. Multiply these out and we get 350. Right, so there's our output energy. Floor buffer produces 350 joules of energy. Your turn, number 1. An arc welder uses 5,200 joules of energy while converting energy at 48% efficiency. Find the welding energy produced by the arc welder. All right, same equation, the tie equation. The arc welder is using 5,200 joules of energy, so that is the input energy. So we got 5,200 here. And then 48% equals 0.48, so we'll multiply by 0.48, and that's going to give us the output energy. So that is 2496, so we multiply that out. 2496, so the arc welder produces 2496 joules of energy. Now the next one we're going to solve to find the efficiency. We've got a lathe that uses 960 joules. So it's using 960, so that is the input energy. So 960 goes in for I. And when you're doing these, make sure to write out the equation first so I know which equation you're using. That's just part of communicating mathematical ideas. Always start with the equation, then plug in your number. So we got 960 here, and it's producing 290 joules, so the output is 290. And we're going to multiply and write by E. All right, so we want to get E by itself, so we're dividing by 960 on both sides. And E equals 0.302, which is, if we convert that to a percent, 30.2%. Oops. Okay, the lathe operates at an efficiency of 30.2%. Your turn number 2. An automobile creates 380 horsepower for acceleration, while the fuel consumed produces 1520 horsepower. Find the efficiency. All right, the energy created for motion, that's 380 joules. And fuel consumed is the input energy, so that is 1,520 times E. All right, divide both sides by 1520. And E equals 0.25. The automobile is, all right, if we convert that to a percent, move that decimal to the right, we get 25%. So the automobile is 25% efficient. Third example, a particular computer chip has an electrical efficiency of 68%. If the chip produces 9.6 watts of computational energy, how much energy does the chip consume? All right, same equation, the tie equation. The efficiency is 68%. So 68% equals 0.68. So that's going to go in for E. The chip produces 9.6 watts of computational energy. All right, production is output, so that is 9.6 over here. And we'll be solving for I. Divide both sides by the number next to the variable. And that gives us I of 14.1. So the chip consumes or uses watts, 14.1 watts. Your turn, number 3. A solar panel produces 196 joules of electrical power. If the panel converts sunlight at an efficiency of 17%, how much power does the panel absorb in sunlight? All right, 17%, 0.17, so we'll plug that in for the efficiency. We don't know the input power, what's coming in sunlight, so that's going to stay I. And the output is 196 joules. So 196 for T. Divide by 0.17 on both sides, and we get I is 1152.9. So the panel absorbs 1,152.9 watts of energy. Oh, that's a mistake. Joules, not watts. Watts was the last problem. Joules of energy. That makes more sense. Now the next application is tolerance. So tolerance is the amount of variation in a product that will still allow it to operate as intended. So a good example is a piston in an internal combustion engine. So if the piston in the cylinder is too large, well, it's not going to fit and the engine's not going to work at all. And if it's too small, there's going to be too big of a gap between the sides of the piston and the sides of the cylinder, and you'll have oil leaking all over the place. So that piston has to be just the right size. But it doesn't have to be perfect. I mean, nothing's ever perfect. So it can vary by just a tiny amount, either too big or too small, and it's still going to work. So in the piston example, the ideal size is 1.494 centimeters. But this piston will work even if it's as big as 1.495 centimeters or 1.493 centimeters. So we have a little bit of leeway there of 0.001 centimeters. So how do we find that leeway, what we call the tolerance? Well, we're going to take either the maximum value minus the ideal, or we could do equals the ideal minus the minimum. So you can subtract the ideal from the maximum or the minimum from the ideal. Either way, you're going to get the same answer. So here we got the max 1.495 minus 1.494, and we get 0.001. And then the same thing here, we get 1.494, the ideal, minus the 1.493 for the minimum, and we get the same answer, 0.001. And both of those are in centimeters. So you don't have to do both the calculations, you can just do one. So here we found the tolerance. I'm just going to call that T for tolerance. And that's the amount the piston can vary in its size. Now we can also express tolerances as a percent. That'll be one of the problems we're going to do, is we're going to take this tolerance expressed as just a number, and one way you could write that is 1.494, the ideal value. And then we use a symbol plus with a minus underneath it. That means plus or minus. And then we put the tolerance, 0.001. And it's in centimeters. So this represents the maximum and minimum values. This is just another way of writing 1.493 and 1.495, because if we take 1.494 and add 0.001, we get the maximum. And if we take 1.494 and subtract 0.001, we get the minimum. So that's one way of writing just the range of acceptable values. But we can also write this as a percent. All right, now we can use the tip equation. the percent tolerance equation. Here's the ideal. So you can take the tolerance equals the ideal times the tolerance expressed as a percentage. Right? So they're both tolerances. One's expressed just as a measurement, in centimeters, or whatever we're measuring in. And this one is expressed as a percentage of the ideal value. So we can convert between the tolerance as a measurement and tolerance as a percent. All right, so let's plug in what we know. We just found the tolerance is 0.001. And we know the ideal value, 1.494. And we're going to multiply it by P. All right, so this is the tip equation. T equals IP. Now solving for P, we'll divide both sides by 1.494. And that gives us a P of 0.000669. And we can round that. Just round it to 67. And finally, we're going to convert this to a percentage. So we'll take this decimal, move it 2 to the right, and we're down to 1 0, so 0.067%. So that means we can write something that looks like this, but with a percent here instead. So I'll write it as 1.494 plus or minus 0.067%, and units are still centimeters. All right, so that's converting from a tolerance to a percent tolerance. Your turn number 4. Police officers have a certain amount of tolerance for motorists exceeding the speed limit. In general, drivers are not stopped for driving within 5 miles per hour of the posted speed limit. If the speed limit on a road is 45, the driver will not be stopped for driving between 40 and 50. Express this tolerance as a percentage. So make sure you can identify the ideal value, the tolerance, and then use the tip equation. So ideal speed is 45. And the tolerance is 5. You can go within 5 miles per hour of 45. So now we use the tip equation. Take the tolerance, plug it in for T. The ideal value is 45. And multiply by P to the percent. Divide by 45 on each side, and we get P equals 0.111. As a percent, that is 11.1%. So our tolerance is 45. Well, the tolerance is 11.1%. And then the range of acceptable values is 45 plus or minus 11.1% miles per hour. All right, we can also do this calculation in the other direction. So we can give it a percentage and ask to find the acceptable range of values. All right, suppose we take our temperature, get a reading of 99.1, which is higher than normal. We're not sure if this indicates whether or not we're sick. So, to be considered normal, a body temperature should be within approximately 1.1% of the average value. The average value being 98.2. So there's your ideal value. So we're going to find the normal range of human body temperatures. So this time, we're given the percentage, and the percentage is 1.1%. So 1.1% is 0.011. So that goes in for P. The ideal value, 98.2. And we're going to find the tolerance. Multiply those out, and we get 1.08. So that means our values should be 98.2 plus or minus 1.08 degrees Fahrenheit. So now we can find the maximum and the minimum value. So we take this ideal value and we're going to add 1.08. And that gives us a maximum of 99.28. So there's the max of the normal range, and the minimum is 98.2 minus 1.08, and that gives us 97.12 degrees Fahrenheit. So any temperature reading between those two is considered normal, and 99.1 is nothing to worry about. Now, I'm no doctor. These are all approximate values, so please don't use these values to try to diagnose yourself. All right, your turn, number 5. What's the range of acceptable weights for a 20-ounce box of cereal if the actual weight must be within 3% of the weight printed on the package? Start with the tip equation. Okay, the ideal value is 20 ounces, so 20 in for the ideal. And the percentage, 3% is 0.03. So multiply that by 0.03. And we get a tolerance then of 0.6. All right, so there's our tolerance, 0.6 ounces. And then the max, actually I'm going to write that as I. So the max will be the ideal plus the tolerance, which is 20 plus 0.6, so 20.6 ounces. And then the minimum is the ideal minus the tolerance, which is 20 minus 0.6, or the minimum is 19.4 ounces. So, the box must contain between 19.4 and 20.6 ounces. Your turn, number 6. The dosage of a patient's heart medication must be within 2% of 15.2 milligrams. What's the safe range of dosages for the heart medication in milligrams? So the ideal dosage is 15.2 milligrams, so 15.2, and 2% is 0.02. So multiply by 0.02 to get the tolerance. And the tolerance then is 0.304 milligrams. So find the max. Ideal plus the tolerance gives us 15.2 is the ideal dosage plus the tolerance of 0.304, and we get 15.504 milligrams. And now for the minimum, that's going to be the ideal minus the tolerance. That is 15.2 minus 0.304, and we get the minimum value of 14.896 milligrams. There's a minimum, maximum, and the tolerance. So the range of safe dosages is between 14.896 milligrams and 15.504 milligrams. So the last topic we have is a percent change. So in the media often see statistics given in the form of a percent change, like population of a certain area has grown by 2.3%, or price of bread is up 12.8%, or something like that. What does that really mean? Well, that's what we're going to find out. And we're going to learn how to calculate it. So the percent change equation is percent change is the amount of change divided by the original amount. All right, the number of customers at a bank increased from 3422 to 3856. What is the percent increase? So the first thing we always want to do in these is, if this is the information we're given, is to find the amount of change. All right, so that's going to be subtraction. We want to find the difference between the new amount and the old amount. So 3856 minus 3422. Now you can always just subtract the smaller number from the larger number, and that will give you a positive value, and then you can just use the context to tell whether or not it's an increase or a decrease. The other way to think about it is to always subtract the old from the new, and if it's positive, it's an increase, and if it's negative, it's a decrease. All right, so we subtract these and we get 434. So that means the percent change, the amount of change over the original amount, that's 434 over the original. Starting number of customers was 3422. Biggest mistake I see on these is dividing by the wrong amount, like dividing by the new number of customers instead of the original number of customers. I divide these out and we get 0.126, which is approximately equal to 0.13. So that is a 13% increase. So the number of bank customers increased by 13%. Your turn number 7. The number of students at Westlake Community College fell from 8517 to 8272. What is the percentage decrease? So we'll calculate the change first. 8517 minus 8272. And for that we get 245. All right, now the percent change is this change, 245 over, right out there. I've already got the original equation here, so let's refer to this. So I'm just going to fill in the numbers now since I already wrote it. 245 over the original amount. Now it fell from 8517 to 8272, so the original amount was 8517. All right, divide those out and we get 0.029, which is, if we take that decimal and move it to the right, we get 2.9, so that's 2.9%. Your enrollment fell by 2.9%. And that's it for today.